Okay, this is the second part of this lecture on hypothesis testing. This part is about testing population mean, meaning we're in the first part we were testing a population proportion. In the second part now in this lecture we are testing population mean. Now when you're testing population mean, just like when we were estimating population mean, we have two options. One of the options is going to be the z-test, if we can use a central limit theorem, and the other option will be a t-test. So when you think about it, how you're going to do that, that's the same story like we have for estimation. Meaning, if you have a normal population and unknown population standard deviation, you will be doing a t-test. In all of the other cases, you will either do a z-test or you will not be able to do anything at all. So that map that you have, that diagram that shows you how do you estimate, and when you end up with the t interval, z interval, you can just simply change the words of estimating into testing, and z interval, t interval into z test or t test. It's the same map in any other respect. Okay? All right, so this is going to be when you are testing claims about the mean. So there will be an initial claim, a null hypothesis that will say the mean is equal to something. Okay? Then you will have alternative hypothesis that will challenge that. It's either going to be the mean is not that something that was claimed, or it's going to be that it's bigger than what is claimed, or that is less than what is claimed. So one of the three, not all three. And depending on whether it's unbiased, which means it's not what was claimed, that will be a two-tailed test, or if the actual mean is bigger than what was claimed, it's going to be the right-tailed test, or if it's smaller, then it's going to be the left-tailed test. The test statistics is going to be another z-value, only this time we're not going to have like the proportion, we're going to have the, not a proportion of the sample, but the mean of the sample. And then you're going to have to subtract the mean of that mean, which is going to be the population mean, presumed to be the one that is in the null hypothesis. And you're going to divide it, of course, with the standard deviation of the sample mean. And we know by the central limit theorem, if we have a central limit theorem, this is a z-value. So if we have a central limit, if you have a chance to make a t-test, it is better to make a t-test in that case. Okay, here is an example. Farmer Bill has grown tomatoes for many years. On average, he had 150 gram tomatoes. Okay, so his tomatoes are somewhat bigger, somewhat smaller, but on average, they're 150 grams. Now, he has done something else. Maybe he changed a fertilizer, maybe changed another hybrid tomato, or new seeds, or whatever. But in the new batch of 45 tomatoes, that's a sample. Notice it's a large sample. The average weight of tomato is 167 grams, more than 150 that was before. Now, can we conclude with the level of significance of 10% that his tomatoes are bigger this year? So we are looking for affirmation of something, acceptance of something. Like in the previous lecture I told you, that can only be alternative hypothesis. We're gonna never accepting the null hypothesis. So this is a setup. The null hypothesis is that it is the same as before. Meaning the tomatoes now are on average 150 grams. Now the sample says it's more. So our alternative is, well, it is more. Because we are asked to, can we conclude that they are bigger than what it was before? So our assumption is that the null hypothesis is that it is as before. The alternative hypothesis, it is more now than it was before. Okay? Test statistic. Test value or the test statistics. That's the formula we have here. This one. It's the same thing here. So the sample mean on the top, 167 minus what was assumed. So this is presumed to be true in the null hypothesis, 150 So 167 is a sample mean, minus 150 is presumed population mean. On the bottom we have radical, or we have variance here of the population. Now we have population standard deviation claimed to be known to be 48 grams, so we can use that. Okay, by the way, you gotta remember that I'm already using algebra here, that when you are having a radical of this, you are doing the radical of the top, which is this, and make too much out of that, well, it's sigma, right? And on the bottom radical, which actually you have to leave it the way it is. Okay, so that's what we are using here. I want to make it nicer. This is a known algebra, right? It should be known to you. When you take a radical of the fraction, take a radical of the top, radical on the bottom. So that's what I have here. I took the radical here, so on the top I have sigma, which is 48, population standard deviation. On the bottom I have radical of sample size, radical of 45. Okay, now you need to work this out. This is really not that hard to calculate. It's something you can easily do. And when you calculate it properly, you end up with 2.3758. That's what I got. So you need to have radical 45, divide 48 with that, and then subtract this 2, which is 17, obviously, and then divide 17 with whatever you got down on the bottom, and you got 2.3758 approximately. Okay, we have a left tail, a right tail test, right tail. Okay, and we have a 10% significance. So we're looking for a right tail of 10% significance. So we're looking for a critical value of the test. The critical value of the test is the number 1.282. How do I know that? Because I know that from the story about estimation, the central area between negative 1.282 and to 1.282 is 80%, which makes this tail here on one side 10% and this tail here 10%. And that's what I'm looking for, right tail of 10%. Okay? Now if you cannot remember that, you can go for t-tables. Right tail is one tail. Probability in one tail. 10% right here. Z value. Right there on the bottom, 1.282. Okay? That's another way to find it. And you can use this table, of course. They're in the textbook as well. So where is our test statistic? Look at this. 2.3758 right here. The test statistics 2.3758, well into the tail. Okay? Which means that the rejection criterion has been met. This has happened. The test value, 2.3758, is well above the critical value, 1.282, which makes the test statistics after the critical value into the tail. That is a rejection. You have this interval here is rejection region. And the probability of test statistics being here is 10%, right? So we are rejecting null hypothesis. What does that mean? It means we are rejecting H0. We are accepting H1, which means we can answer, yeah, his tomatoes are bigger this year. On average, his tomatoes are bigger this year. Okay? So that's what we were asking when you're answering the question. His tomatoes are bigger because we just concluded that we are rejecting null hypothesis, which also means acceptance of the alternative. Okay, one more. A sample of 120 men frequenting certain local bars shows their average education level is 12.3 and standard deviation is 2.6. That's all sample data. Sample mean, sample standard deviation. The average education in the United States, 13 years of schooling. Okay, so, elementary school plus high school plus apparently 1 year of college, something like that. Okay? Can we conclude that the men in our local bar are less educated than population on average, using 1% significance level? Okay, so one more time, we are asked to confirm something. So that's going to be alternative hypothesis. Okay, so the null hypothesis is that the average education level of these guys attending this bar is 13. Just like a general population. So that's null hypothesis, and we are looking to reject it, to show that that is false, right? The alternative hypothesis is left tail. That is actually less. Why? Because in our sample we have 12.3. That's a 0.7 years less. It's not a big difference, but in our sample, as an indication, it's less. So you could choose left tail test, left tail alternative hypothesis. Right tail makes no sense because that would mean that you would assume it's more than 13, and that you don't have any evidence for that. Or you can choose unbiased two tail. It's just not 13. Since we have this educated bias here from the sample, we think we should take left tail alternative. You could take unbiased always if you like. Okay. So now the test statistics. So the test statistics is always the same thing here. Again, that is in a formula we stated in the very beginning. The z-value, this must be a z-random variable. Z-value, if you take one sample, and we just have to calculate what it is. So the sample mean 12.3. The presumed value for the population mean, presume, because we are assuming that H0 is true, right? We are allowing that to happen. We're going to hang that hypothesis with its own tail. It's like you're trying somebody, you use his own testimony against him. All right, so that's 13. Down on the bottom, I need to have, again, so I'm using, when you take the radical out of this expression, you're using this. Okay, 2.6. Well, that's not a population standard deviation. That's a sample standard deviation. So what am I doing here? Well, I am allowing that because I have a very large sample, 120, not very large, large sample. So I'm allowed to change population standard deviation with sample standard deviation. Substitution is okay. Right? Only if you have large sample. That's another limit theorem that we use often when we don't have information on population standard deviation. You could say, well, why don't you just simply use t-test? Well, I don't know that education is distributed normally. I don't. And I actually don't believe it is. So there's no information about that. To use t-test, I need to know that the population, that would be education level, is distributed from person to person in a bell curve distribution. I don't think it is. There's no reason to believe. We can actually argue exactly the opposite. It's distributed in a skewed format, not in a symmetric format. So, one way or the other, we have to do the z-test, and we have to replace this value here with S, and that's what we are doing. So we get an approximation. Okay. I should also notice that this is immediately becoming a wiggle rather than exactly equal. Okay. But one way or the other, you can really calculate it. The radical of 120 to 2.6 divided with whatever that is, that radical, and then you get something for the denominator. On the top, you have negative 0.7 divided with that what you calculate on the bottom. I ended up with negative 2.95. Okay, what's the critical value of the test? Well, the critical value of the test is the left tail critical value, where the left tail is equal to 1%, which means I'm looking for this picture. You always need to have this picture in mind, what you're looking for. Left tail test. We are looking for the critical value. We need this number here, so that this stuff here, this area is going to be 1%. The picture doesn't have to be precise, and mine certainly isn't, right? 0.01. Okay, now I do remember when you have a central area of 98%, you get 1% here, 1% here. This is what we are looking for. What's that critical value with 98% central confidence. That would be 2.326. And again, you can look at the tables. Probability one tail, in this case left tail, is 1%. Z value 2.326. You do have to think, because here you need to have negative. It's below zero, right? Zero is here. The table tells you, a critical value that is positive, but in this particular case, it's actually negative. You can say also 2.33 if you like. That's just remembering 2 decimals as opposed to 3, which is what I have here. It won't change the conclusion. And our test value is here. In the tail. It's definitely below negative 2.326. It's smaller. You see, negative 2.33. This guy is smaller as a negative number, right? It's smaller than a critical value of the test, which means we have rejection. So the test value is in the tail here, and we have rejection approximately. I don't know, maybe it's a little closer here, but it's in the tail one way or the other. So what we have here is a rejection of the null hypothesis, which also means that assumption that these guys attending this bar are the equally educated as general population, which will be 13 years of age. 13 years of education. It's not true. They are less educated. They are less educated than average person in a population. Average adult men, because they're men. Average men in the population. Okay. So that's our conclusion. The picture is always necessary. The sketch, not necessarily a great. In here I didn't do it like I did in the previous example, but you need to make it to make sure you understand what you're dealing with. Okay. Let's go one more. Insurance companies reviewing current policy rates. The original setting for the charge a premium was because the average claim for that particular insurance was $3,500. So I don't know, that could be a car accident or something else. They are concerned that actually went higher. So they probably are going to lose a lot of money if they don't increase premium, right? So they're going to increase premium, but they can't just do it, whatever they think, because there's competition. There's a competition, so they need to, figure out what is economically okay for them in the business sense, right? So they are selecting randomly 80 claims to calculate, to find out what was the, so that's like a maybe nationwide company, so, claims all over the place. So they're going to find out 80 at random to find out what was that average in the sample. And it seems to be that the sample is confirming their suspicion that might went up. In the sample they have 3,720, which is more than 3,500. So also assume the standard deviation of the claim 1,450. It's a large standard deviation, but of course it happens when you car accident. Sometimes it's a lot more, sometimes it's fender bender. So significance level of 5% is something we're going to use as well, and find out whether the claim actually went up. The average claim. So this is again the average of the population of the claims for this insurance company. It's a mean of the population. So that's what we are testing. The setup of the test is, it is as before. So it's still 3,500. Okay? The sample indication is it's more. It went up. The mean claim is more than 3,500. Okay. The rest of that is again the calculation by using the test statistics, and it's always the same test statistics for z-test, this one. The sample mean, 3720. Presumed mean claim. In the past, right, we presume it's still there, 3,500. Downstairs, again, you have the this guy. downstairs, right? Take a radical. I always write that in the form before you take a radical. But once you take a radical, is this guy. So it's gonna be 1450 radical of 80 sample size. Okay, so we are now calculating this, yada yada yada. You get 1.357, but the rejection region should start at 1.645. How? Again, this is 5%, because this is 95%. So again, you can find it in a table, or you can think about it. You remember that estimation theory story. Negative 1.645, positive 1.645 is 90%. So there might be 5% in the tail here. So that's 95% here. Therefore, this is 5%. Test statistics is not in the tail. 1.357. Test statistic is not in the tail. Which means when we set up tests like that, we cannot claim. You can say, well, I don't believe, I think it's went up. Well, whatever you believe or not, you don't have enough evidence to claim that it changed. So it looks like your sample went up, but it didn't went up enough to claim that it changed. So you don't have enough statistical evidence to claim that it went up. You don't have enough statistical evidence to reject this guy. The test statistic is not in the tail, has not passed the critical value of the test. So in your setup, you have no enough statistical evidence. You can say, oh, let me just use now, 10% significance level. Well, you can't do like that. I mean, you have to set up the test from the get-go. You're not adjusting the test whatever you like. So if the setup was for 5% significance level, you don't have enough. If the setup would be for 10% significance level, then the critical value would change, it would be 1.282, and this thing would pass 1.282. Oh, then you would have a rejection, right? But you allow the probability of type 1 error to you making a rejection, the probability that you're actually making a wrong rejection, that the initial claim doesn't change, but you're making a rejection, went up. It's now up to 10%. The probability of type 1 error is up to 10%. So in here, in this test, is no more than 5%. So it's more stringent test. Okay, so you can see here, there are some relativities here in conclusions. But the conclusion is always tied up with the level of significance. So you need to know, if you're rejecting the initial claim, what is your confidence that you're correctly rejecting initial claim? That is the alternative to the complementary to the level of significance. So if I would be rejecting here, I could not be stating that I'm at 95%, at least 95% confidence. Nope. Right? But if I would be using a 10% significance level, then I would reject. And I was so there's some relativity here. Okay. What about t-test? Well, in the t-test, the story goes that if you have a conditions for the use of t-random variable, that this will be a t-random variable, that means that the population has to be distributed normally, and you don't know the population standard deviation, so you use S basically in the random variable. So we know that from the story before, this turns out to be t-random variable. So you're going to be doing all the same as before. The only difference is that you're going to be using the critical values that are t critical values, not the z critical value, because this is, in that case, t-random variable. Again, you got to remember that the conditions to do the t-test is the same as the conditions to do the t-estimate. Population must be distributed normally, and the population standard deviation must be unknown. If you don't have those two, you cannot do t-test. You have to do something else. T-test about the mean. There's some rejection criteria, but I'm going to explain that rather with the pictures here. So here is an example. It's usually done when you have small samples. Let X be the tumor growth in millimeter per day induced in a lab animal. Okay, we have measurements in 9 consecutive days. There is consecutive days. There is a reason to believe the tumor growth follows normal distribution with mean 4 and unknown standard deviation. That's in millimeters. So it's a small measure. So the tumor grows day on day, on average, at least somebody says that, 4 millimeters. Okay, we have a sample of 9, maybe a 9 mice or 9 days, I don't know. And that shows up mean of 4.7 millimeters per day. Bigger than what was assumed before. Okay, this was induced to mouse was either, I don't know, have some genetic modification or maybe was given some chemical to get that tumor growing. Not a nice thing to happen, but it happens in lab condition. They're doing stuff like that. Okay, so we have 4.7 millimeters and sample standard deviation is 1.2 millimeters. You immediately notice you don't have population standard deviation because there is a sample standard deviation here. You also notice you have a small sample. So you can't replace the population standard deviation with the sample standard deviation you would do for the t-test because the sample is small. So we have a problem, right? But the tumor growth is by the normal distribution. It says in the problem. Excellent. So we have a T conditions for the t-test. Okay. So what do we assume as a null hypothesis? We assume as a null hypothesis that the tumor growth was as claimed before. Somebody claimed it's 4 millimeters per day. Now we have in our lab more. So we are going to have alternative hypothesis it's more than 4 millimeters per day because in our sample is 4.7. Okay? Now you have these test statistics that we have mentioned before. The same test statistics we have from the get-go. The only difference is that we are replacing sigma with S, the sample standard deviation. So you're going to calculate that. And so this would be, we have 4.7 on the top, the mean of the sample, minus the mean in the null hypothesis 4, presumed to be true, the mean of the population, divided with the, when you take a radical of this, is going to be S divided with radical n. And okay, we already know what S is. It's 1.2. So this is taking a radical, right? Or you can just simply, calculate this and then take radical after. And down there we have the sample size, radical n, that would be 9. So it's 1.2 divided with 3, actually. So that's 0.4. So you have to do 4.7 minus 4 divided with 0.4. And when you do that, you get 1.75. 1.75 is the test value, the test statistic, or the test value. We have these alternative names for the same thing. The critical value of the test is to be found in t-tables. 9 is a sample size. Our test is right tail test. One tail. 9 sample size means 8 degrees of freedom. We're going to use 5% significance level in one tail because our test is right tail test. The number we are looking for a critical value is 1.860. 1 point, by the way, you can find it down there, right? At the bottom. We're not using z-test, we're using a t-test, 860. That's a critical value. Here's a picture of the test. So this is a T-curve with 8 degrees of freedom. The critical value is here, 1.86, 1.860, 1.86, right? This is 5%. This tail is 5%. But test statistic is not in the tail. The test statistic is 1.75, which is before the tail starts. The tail starts at 1.86. So the test statistics is 1.75 before that. It didn't pass the 0.86. 0.75 before that. It didn't pass the critical value. So it should if you want to reject a null hypothesis, this number should be bigger than this number. It should be in the tail, bigger than 1.86. It isn't. Okay. Conclusion: you don't have enough evidence to reject a null hypothesis. So whoever wrote that before and stated that this situation induces 4 millimeter tumor growth a day in a lab animal could be right. We don't know. We don't have enough evidence to claim it's more. So maybe maybe there's some kind of chemical given to that mouse. It's very toxic, and we would like to conclude it's more toxic than anybody thought before. But we don't have enough evidence. Okay, what do you need to do? Well, you need to get more mice. You need to get more days, and so on. Maybe you can get more days because mice. Well, and you need to get more mice, but you need to increase sample size because obviously we could not reject the null hypothesis. And we could suspect that this is indeed the case. We should be able to reject it. But we don't have enough evidence to do that. And no enough evidence, you don't have this difference to be that big, 4.7 and 4, or you don't have enough days. You get a bigger sample. Maybe you'll get, with a bigger sample, you get more evidence. Okay? Here's another one. United States National Research Council currently recommends that females between ages 11 and 50, so we can call it childbearing age, of course, should be taking 15 milligrams of iron daily, right? So that's because of the bleeding, right? So you get replenish the blood with the iron because the blood needs an iron to be able to build up red blood cells because they're red because of the oxidation that iron takes an oxygen and binds to an oxygen and becomes red. Iron with just like rust, iron with the oxygen becomes red, oxidized iron. So the recommendation is from United States National Research Council that they would be taking 15 milligrams iron daily. Okay, so now we are getting 55 female researchers. This is somewhat biased. Well, we think, they might be a little more careful about their diet, right? And we found, after taking long diaries from them, that they are taking, on average, 14.1 milligrams. So it seems to be very close to 15. So you might think about, well, apparently we are not going to be, able to conclude that they are deficient, iron deficient, right? Maybe they are, maybe they aren't, we don't know. So the sample standard deviation also in this sample was 2.367 milligrams. Can we conclude that average intake of American female is less than what is recommended? You could say, what's that got to do with American female? Okay, I'm thinking like this. If we can show that female researchers are iron deficient, they are not taking enough irons, and we are kind of expect that they should be more concerned about their diet, probably even worse. All right, so that's our take here. Okay, so let's do the test. What do we have? 25 is not big enough. Okay, but we can assume normal distribution of iron from female to female. Okay, so we have a normal population. We don't have a population standard deviation. The only standard deviation we have here is a sample standard deviation. It's just stated here, sample standard deviation. Unknown population standard deviation. So you have this, what you want. You have conditions for the t-test. Because you would not be able to do the z-test. Okay? The sample size is too small, and you don't have the population standard deviation. So that it has to go in the formula for z-test, and you don't have that. You don't have that sigma. And you cannot replace it with s because the sample size is small. So you have to use t-test. But you do have conditions for the t-test. Population is normal, and the population standard deviation is unknown. Two conditions. Okay? We're going to use also a level of significance of 5%. So if we reject the null hypothesis, we want to be at least 95% sure. Okay? This is our test. We will assume that American females are not iron deficient, so which means they're eating 80 milligrams of iron daily. We will have alternative hypothesis that is biased from our sample. Well, they are iron deficient, they're eating less because our female researchers are getting less. Okay, 14.1. And here's the test statistics. And one more time, again, I have to point this out that when you take a radical, some people are going to be puzzled with that. When you take a radical of a fraction, you get the radical on the top, just to get rid of the square, and radical on the bottom will stay what it is. Okay? And so that's what I'm writing here. On the top, of course, I have a sample mean, which is 14.1. Presumed, 15. Presumed, null hypothesis claim population mean of 15. Downstairs, I have this S 2.367 divided with radical of 25, the sample size. That's just 5 here. So this whole calculation ends up with negative 1.901. I think this is approximation, but maybe it isn't. I don't know. I think it's approximation, so maybe I should put wiggle here. All right. What's my critical value of the test, right? So I have the test value. Is the test value in the tail? But what tail? I need to find the critical value. Okay. So the critical value of the test. Sample size is 25. That means degrees of freedom is 24. This is a t-test, one tail, left tail test. T-tables, 5% in left tail, 25, 24 degrees of freedom, n is 25, 24 is degrees of freedom. The number we are looking for is this number here, 1.711. But you can see on my picture, very nice. Here, this is the critical value. This guy, and of course it's negative this time, because you have to notice that, because it's going to be in the left tail, so it's going to be on the left side, there's all negative numbers. This is 0, and here are positive numbers. So the table doesn't tell you is it positive or negative. You got to think about it. It says one tail. Now, which tail? Left tail, right tail, right? Negative 1.901. Is our test statistics. Critical value is negative 1.711. The test statistic is definitely in the tail here. It's below. It passes the critical value, which means rejection. Statistic is definitely in the tail here. It's rejection of the null hypothesis. Females are not, or at least researchers, are not iron deficient. They're taking 15 milligrams as was recommended. Well, they are deficient because we just rejected this guy, which means we are accepting alternatives. So we are claiming American females are eating less iron than what is recommended by United States National Research Council. Okay, they are recommending 50 milligrams of iron daily, but they're not researchers, and we can generally conclude that general population is probably even going to be worse. Okay? Now, if you use your calculator will give you p-value. And I said before, to reject a null hypothesis, the p-value, that's a rule of thumb from the previous lecture, which is the same thing here. The p, which is what your calculator will give you, must be less than the level of significance. So this is rejection criterion. If you have that, then you reject the null hypothesis. That's what happens here. The p-value is 3.5%, which is less than 5%. Okay? That is if you use your calculator, because your calculator is not interested in any level of significance, it's just going to give you the p-value. And then you think, what your level of significance is, which you can say here. If I use level of significance of 5%, I will reject. If I use 1%, I won't. Why? Because 3.5% is not less than 1%. But since we use 5%, you can reject. So I am at least 95% or more confident that our rejection, that our claim that American female are not eating enough iron is correct. Right? But if you ask me, are you going to be 99% sure? Nah, I don't know. I'm not 99% sure, but I'm at least 95% sure. Okay? So how you do that with a calculator? Right, you just basically use the testing, statistical testing, and we are doing the test of the mean. We're doing t-test. You must know whether you're doing z-test or t-test because there are different options, of course. Input, you have data on stats. We have stats, which means we have all of the numbers. If you have raw data like this female took this, that female took that, then you have a number for 1, for 2, for 3. That would be raw data. We don't have that. We have stats. And then immediately I ask you, if you have stats, what did you assume? Well, we assume 15 for the mean. What do you have from your sample? Mean of the sample, X bar, right? 14.1. The next thing I ask you, what do you have for standard deviation? Well. We had the 2.367. Okay. What's your size of the sample? 25. What did you use as a two tail, left tail, right tail? Well, we use left tail. So you have to select that. Calculate. That's it. It will also draw a picture like me, but as a matter of fact, it will give you this, not this picture with the level of significance. It didn't ask for that. It will give you this picture. Okay, but I have a better picture here, so I'm not going to show you how. You can check it out. Test value 1.901 negative. I got the same thing here, only more decimals actually. The p-value of the test, this is not a p, it's not a proportion. We have no proportions here, right? I said already the calculator uses this p symbol, which is kind of it's not a correct symbol to use. There should be p-value, like we write here, p-value. But that, you need to get used to that. So that is 0.03467 blah blah blah. That's a 3.5% approximately, 3.5%. And that is less than the level of significance. So you make a decision now. You get less than 5%, so you reject the null hypothesis, which means you're accepting the alternative. Right? The mean of the sample, that's, we just wrote that. So this is, in case you have data, then it's going to calculate the mean and the standard deviation of the sample, which is a helpful thing to do, right? If you didn't calculate it yourself. And down there you have the sample size, 25, you already know that as well. So again, if you have some lots of data with a frequency list, this one is 10 times, this one is 50 times and whatnot, then maybe it's difficult to find it out. So, your calculator will tell you that, all right? Well, one way. Now, by the way, so again, in this particular case, we're using rule of thumb, p-value of the test. Calculator will give you that. You would not be able to find it yourself because you need to use a calculator, so you have to have a tables for the 24 degrees of freedom t random variable distribution, and we don't have that. We just have some critical values, but we don't have all possible p-values you can find. And but out of this 3.5% is less than 5%, we would still be rejecting, just like we did with our own calculation. All right? That's the story, the end of the story about the t-testing and z-testing. Okay? There is one homework on testing, only one. So we have population mean by using the z-test, population mean by using a t-test. 3 different tests you can make. And you can use the same logic for that diagram that we use for estimation. If you remember, when we're doing estimation, of course you need to remember that because we had that not very long ago. You can use the same diagram for testing. You will not be looking for confidence interval, you'll be looking for test. So instead of confidence interval, you're doing the test here. The same blah 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 blah. You end up with z-test. You end up with t-test. You end up with z-test. Z-test here, the rest is the same. Z-test, z-test. Right? Exactly the same diagram, only you change confidence interval with test. So this is a z confidence interval, so z-test. The rest, whatever is in between, is exactly the same. So you're testing a population mean, you're testing population proportion. You're either going to end up with a t-test or you're going to end up with a z-test. This is the same, the same diagram, only with the different words. Instead of interval, it's a test. So you can use that. But that's what we were doing. Testing population proportion, testing population mean by using either z-test or a t-test. 3 different tests. And each test, of course, could be left tail, right tail, or 2-tail test. Right? So that's your homework. So to do your homework will be to practice these types of problems. And notice also in the homework, the author of the textbook will ask you the questions about the claims. And in your setup of every test, there are 2 claims. One of them is null claim, the null hypothesis, and one of them is alternative hypothesis, alternative claim. Okay? They are equal in terms of importance. So sometimes the question is about null claim, sometimes the question is about alternative claim. You think about it. The test is always about rejecting or not rejecting null claim, which means at the same time accepting or not accepting the alternative claim. So if you need to accept something, there's going to be alternative claim. If you need to reject something, that's null claim. That's the setup of the test. The testing values are 1 value for testing proportion mean with z-test and 1 value for testing mean with t-test. But there are formulas, of course, so it's easy. The critical values for the tests are z critical value for the testing proportion, z critical value for testing mean by using z-test, and t critical value by using a testing mean by using t-test. Again, I know it's confusing when you meet it first time, but that's how it works. Okay, we're not going to be doing anything else, so this is it. This is going to be 1 question in the final test on all 3. I'm not going to tell you which one. But there is also a homework, which is completely extra credit homework. Again, I can add up lots of points